Inflection point is where concavity changes. It's when we change the second derivative from being positive to negative or vice versa. So you want to watch out for this. You want to set it equal to 0 to find potential inflection points, just like we find potential critical points when we set the first derivative equal to 0. But then you've got to test it to see whether we actually do change our second derivative from being positive to negative or vice versa. So if we're going to find potential inflection points, we want to find the second derivative. So here comes the first derivative. And then the second derivative. And then we set the second derivative equal to 0 to find our potential inflection points. But remember, we got to still test them. So if I'm going to solve that equation, I want to factor out a 10x. And then set each factored piece equal to 0. Then we get 0 equals 2x to the third minus 3. And then if you solve this, you get x is 0. And if you solve this, you get x is, let's see, 3 over 2. And then it's, wait, is it cubed root? I copied that down wrong. That should be squared, right? Because we factor out an x. So if you solve that equation, you should get the square root. And then it's positive or negative. Anytime you use the square root to cancel out a squared. I'll just do that algebra out just to make sure I don't lose anybody. I added 3 to both sides. Divide 2 from both sides. And then here, when you use a square root to cancel out a squared, you got to consider both the positive and negative. We have 3 potential inflection points. To test them, let's put them on a number line, and we'll check the second derivative between each of them. Because remember, the whole point of an inflection point, it's an inflection point if the second derivative changes. And there's some other tricks that you can do too to find out inflection points that can make the calculation a little easier, but I like to hammer home the idea of an inflection point. The definition of an inflection point is a location where we change concavity, so where the second derivative goes from positive to negative or vice versa. What is this? 3 over 2 square root. Okay, so let's test a point further to the left, because these are the only places where we could switch concavity. Okay, let's try x equals negative 2. We don't really care what the result is. We just want to know whether it's positive or negative. So if I plug in negative 2 in here, into the second derivative, that's going to give me negative 2 cubed is negative 8. So negative 8 times 20 gives me negative 160. And this is negative 2 times negative 30 makes positive 60. So we're going to get a negative number if I plug in negative 2. So it's negative over here. And then here's our first potential inflection point. Let's test something in between. Let's test x equals negative 1. To see if it switched directions. So I'm going to go up into my function, see what happens, into my second derivative, I should say, and see what happens when I plug in negative 1. Negative 1 cubed is negative 1. 20 times negative 1 is negative 20. Negative 20 is going to be plus 30 because negative times a negative. It's going to give us a positive 10, so it's positive here. So the negative square root of 3 over 2 is an inflection point. Then we want to test between 0 and square root of 3 over 2. So let's test positive 1. If I plug in 1 into the second derivative, that's 20 minus 30 makes negative. So it did switch directions again. And then I want to test a value to the right of this other inflection point, see if we switch signs again. I'm plugging in 2 into the second derivative. So 2 cubed makes 8. 8 times 20 makes 160. So we got, 160 minus 60 is still going to be positive. So we switched direction again. Okay, so negative to positive, positive to negative, negative to positive. So this is an inflection point, 0 is an inflection point, and square root of 3 over 2 is also an inflection point because concavity changes, the second derivative changes.